Yesterday, I introduced a gave you a basic introduction, and then Bertel pushed through with computing some equilibrium, and Victor discussed fixed effects in these dynamic discrete choice models. I want to continue in that spirit by thinking about two other issues that are pretty important in the estimation of these kinds of models. The first is, how many conditional choice probabilities do you actually have to estimate if you're going to take that route in terms of using a CCP method to estimate the model? Do you have to go right to the end of the person's life cycle? And the answer is no. And so I'm going to introduce that, and then Victor's going to be talking more about that next lecture. Oh. Next, the other issue I want to introduce is what happens when the conditional independence assumption doesn't hold? How do we go about things then? Because that starts to make things much more problematic, because now you're not conditioning on all the state variables that affect the agent just before he or she sees those epsilons, those type 1 extreme logic type shocks. So that really messes things up a lot in principle, because as you can imagine, if you've got some unobserved heterogeneity in the background, and you don't have the conditions that allow you to do some kind of fixed effect estimator, so that you are restricted even in terms of the way you introduce random, the unobserved heterogeneity, you still have computational problems, because you have to think about how you do the integration or how you deal with that aspect. And so that's the second part of this lecture. So they're really two distinct parts. And so it's almost too many lectures, but no break in between. Sorry. So first part. We see that estimating all these dynamic discrete choice models is to some extent complicated by the fact that you have to get the CCPs. If a property called finite dependence holds, then the number of CCPs that you actually have to calculate is greatly reduced. Now, practically all applications exploit some form of finite dependence. Now, that is a reflection of not so much, I think, that any problem that you can think of has finite dependence. I don't think that's the reason. I think the reason is that people really want finite dependence to hold so that they don't have to compute a whole lot of CCPs in the future. And so they structure the problem so that finite dependence does hold. That's how I think the literature's proceeded. There's nothing wrong with that. One of the first things you learn in economics is that there are constraints. So you look for what is feasible, okay? And that goes to your research as well. You do stuff that is feasible, not try and do stuff that's infeasible. And of course, the problem with research is you don't know which is which. So intuitively, what we mean by finite dependence, and it's in the italics there, is that when you're thinking about taking one action, watch my hands, versus another action, and if you followed through a weighted sequence of actions from then on out that are not optimal, but are reflecting that weighting sequence that I was talking about before, and which we'll revisit again in a few minutes. You start out with one weighting sequence over here, and you end up with a distribution of state variables over here, there. Or you could start out with another action, and I should say, as you telescope forward using another set of actions, say you end up at the same distribution a few periods hence. Think of what that means intuitively. We're asking this guy to take action J versus action K. And we're trying to work out, how do we calculate, compute the conditional valuation function for each of these two actions? Because if we can do that, then we're right back to almost the static dependent world, where we've got V plus epsilon greater than or equal, Vj plus epsilon j greater than or equal to Vk plus epsilon k, where the V is the conditional value functions now. We've done the telescoping, which you all know about, because I know you spent tons of time reviewing all the lecture notes last night. And you're thinking, how do we make those two come together? If they don't come together, they will eventually come together at cat T when there's nothing left, because then you're just calculating a value function one way, value function the other way, using this telescoping method. Then you're fine, but that could be a long way out. So maybe you only have to go a few periods out. Actually, we've already done one of these examples straight off when we did Rust's example of Mr. Zerker. We had a renewal problem. And basically what we said was, suppose we look at these two valuation functions of maintain versus replace engine. And then we said, how do we express those things so that we can look at the difference in a nice, easy way? And what we found was, I didn't emphasize this at all, but what we found was that if the guy replaces the engine today and then replaces the engine tomorrow, he would end up at that point with the same social surplus function that he would get if he maintained the engine today, different action, but replaced the action tomorrow, because in both periods, in both scenarios, you would end up with a new engine 2 periods hence. That's what we mean by finite dependence. It might not be 2 periods hence, but that's what we mean by finite dependence. In other words, we didn't have to calculate, we didn't have to telescope out forever. In order to we did not have to telescope right out to the end of the person's life, Mr. Zerker's or the bus's. We only had to calculate out 1 period hence. That is the notion behind finite dependence. Okay. One thing that is worth pointing out straight off is that this finite dependence property has something to do with the transitions of the underlying state variables that you observe. It has nothing to do with the optimization behavior. And as a result of that, you can calculate whether there's finite dependence or not by first just looking or focusing on the transition functions to see whether it holds. And then if it does hold for some number of periods, you'd have to calculate out the conditional choice probabilities as far as that. Now, I'm going to go through this in a minute, as in right now, but it's worth talking about first in a hand-wavy type sense. All right, so we got the standard model here. T could be infinity, so that in that case, we're talking about stationary model, perhaps. X, as before, is just going to be a set of finite set of variables. And here I want to mention that when Whitney talks this afternoon, he will be focusing on dynamic discrete choice models, for example, in which X is not coming from a finite set. And then he'll be thinking about, well, how do you do the correction to deal with what I'll call the asymptotic bias associated, well, everyone calls the asymptotic bias associated with what happens when you do a kernel estimation of a bigger space when X comes from a bigger space. In other words, the basic principles of what we're teaching you are being taught by most of us in terms of discrete spaces. But actually what Whitney's doing is saying, hey, this extends, and this is how you do it, okay? Go back to the discrete choices. I gave you a little feel for how you would extend to continuous choices yesterday. And we've got the same kind of transitions. We haven't checked whether we're coordinating notation across lectures, but can't do everything. So here's our xt and xt plus 1 conditional on action j. And then we've got something like this standard setup that things have to be sort of bounded in some the sequence itself has to be bounded. So and really the only reason for that is it's really hard to subtract a negative infinity to add a negative infinity to a positive infinity. That's what you have to, that's where you run into these kind of problems that, you know, you can't do Lebesgue integration basically. And so here's our discount factor and our utility. Here are the things that we use this. Here are our here are the stuff we observe. Only one of these is going to be 1 each period. The others are going to be 0. And here is our disturbance, okay? Same as before. So we've got an optimal decision rule with a little O there for optimal. And then we have a conditional choice probability that says, what's the probability that he'll pick this, given that we only see the x's, that we're going to integrate over the epsilons. We're assuming conditional independence. We've got a value, we've got a social surplus function to reflect, okay, this is what he's going to get over his lifetime. And here's the conditional value function in which we have the systematic part of current utility, plus here is the expected surplus function for tomorrow, expected because we don't know what tomorrow's state variables are going to be, and we're discounting by beta. And then we have, after that, the conditional value function correction, which is the difference between the social surplus function and the conditional value function, okay? And I've emphasized that this object is really important because it's identified. And then we can then exploit that to show what else is identified and go from there. Now, I also defined this weight sequence, which, and a couple of you pointed out to me, well, wait a minute, why do you even need to go this far in terms of defining this generalized weight sequence? You're not even using it in the identification. Absolutely right. I wasn't. I was picking I could have picked a lot of different weight sequences, but yesterday I picked a very specific weight sequence of taking action J now and then say picking action 1 from then on out. That was a weight sequence that I picked to establish the identification. And then when we're talking about the observational equivalence, I was talking about picking action J now and then picking whatever action was associated with the normalization that you're doing when we're doing that representation, the observational equivalence. Now, I realize that some of this stuff is sounding like garbage to you, but if you go back and look at the lecture notes and then compare with what I'm saying now, you will get it, okay? It takes work, not just listening. Sorry to be sort of so pushy like that, but that's the way it is. Sorry in the usual. I'm not sorry at all, but I want you to do it. So here we have it. These weights are finite. They sum to 1. They could be negative. And we have this kappa thing that says, well, this is how the state variables move when you follow a particular type of sequence. And I'll put this up with an omega now to reflect the fact that what your distribution of x's is going to be in the future depends on not only what you start with, in terms of here you are at xt and here t and taking action j to begin with, but also the weight sequence that you're going to use from then on out to get what I'm going to call the distribution of weights, and they're potentially negative by the time you reach xt plus, the probability that you'll reach xt plus 1, or that particular value of x in period t plus 1. And so we define it recursively, as I said before, and you can see that none of this stuff depends on optimizing behavior. And that's what I mean when I'm going to repeat again later, hey, finite dependence doesn't depend on optimizing behavior. It's something that you do outside the model beforehand. assume once you have the conditional, if the conditional independence assumption holds. So that's how that works. Now, if we push that representation thing that I was talking about yesterday, okay, we have that, the difference between, sorry, the social surplus function is equal to the conditional value function plus the this value function correction term. Okay, we defined it that way, and then we said this thing was identified. I gave you a couple of examples of how it works. All right, and we can now expand this thing out, and so let's just telescope away by taking action K in the first period, action J in the next period, or whatever the weight sequence is telling us to do. Remember, it could be anything that's providing these weights add up to 1. And so we've got current utility plus, and let's not go right to the end of the person's lifetime. Let's just go to this far out, row periods out. So we are following this telescoping stuff that I did yesterday, okay, where we're saying, well, what's the probability of reaching X tau after tau periods into the future, okay? And then from tau periods, how do we go to tau plus 1? Keep on going through until you reach T plus rho, okay? So remember, in that last lecture, I said, how do you do it for one period forward when you're taking action K? And then I said, you know, you could have took any combination of these things, provided they add up to 1. And not only that, you can keep on going. And that gave us the representation for going from T right to the end. And now I'm saying, let's not go right to the end. Let's just go out to go out row periods. So this far, not the whole way. All right. So here we have the social surplus capturing value from, where is it? From here on out, and where we could have reached X with this kind of weight. Here is the probability distribution. I say weight, really, of reaching X by following this particular omega path prescribed, you know, a half here, half there, maybe 3/4, quarter, whatever. And here are the correction terms for the non-optimal behavior, which we know are identified, because we saw that from last period. And then we're going to go the following route. We're going to say, suppose it's true that if you follow one weight sequence for J, and for starting out with action J, and then another weight sequence for action K, notice 2 different weight sequences, one for J and one for K, okay. Is it possible that we could choose our weight sequence so that once we reach this point, row periods out, these guys will see this be the same and cancel? That is what I mean by you reach your tau periods out, or row periods out, I should say. The distribution of the X's is the same, regardless of whether you start with J or whether you start with K, because you've chosen 2 different weight sequences that somehow bring them back together. Now, remember in the bus example, I said, maintain, replace, gives you the same distribution of the value, same social surplus function as replace, because in both periods, you get back to new bus after 3rd period. And so everything's the same, and it's degenerate. It's not even a probability distribution in that case, okay? I'll give you another simple example. Suppose you depreciate human capital a little bit each period, and after, say, by not working or something, after, say, 4 periods, it's all gone, all right? So we're thinking about someone who chooses between working now and not working now. How do we get the difference in those conditional value functions? Well, here we go. We go out and we say, well, this thing can be expanded. And so we're going to go out a few periods, as many periods, say like 4, as it takes to depreciate the human capital back to 0 when the person initially chooses to work. So you got woman's thinking about, do I work now or not? So one sequence would be work now, but stop. Another sequence is stop 5 times, stop, okay? And that way, after 5 periods, this person will have the same amount of human capital, regardless of whether she goes this way or that way. Now, you might be thinking, wait a minute, that's not optimal to even think about the problem that way. And my answer is, of course, you're right. And that's exactly why we have these value function correction terms in there, because that value function correction is telling us the difference between the conditional value function and the social surplus function, which is what we're really interested in. So it's not simply that they're taking different weight sequences. As a result of that, they are also going to be getting different value function correction terms, and that thing is going to be capturing partly, along with the utilities that you score on the way, the difference between the lifetime of going one way versus the lifetime of going the other. Okay? You could say it was a mathematical trick, if you like, I don't care. But the basic point is there's so much structure on the problem as it is with the conditional independence assumption, and in this case, the finite dependence assumption that you depreciate after several periods, that in the end, you only have to simulate or compute when you're telescoping out the difference between 2 conditional value functions. You only have to go 4 or 5 periods in the example that I've just given you in order to be able to capture or characterize or represent, means the same thing, the difference in these conditional value functions from going one way or the other. And that is used a lot of times, not just in the labor literature, but also in the IO literature. Okay? So let's move on with a little bit more notation here. We got finite dependence. If there are a set of weights, here they are. Here you start out at I with xt and t, and here you start out at j, xt and t, set of weights, so that after row periods, this weight distribution is the same. And as a result of that, when you're taking the stuff for I, replace all the j's with I along here. Okay, I'm not going to do it, but replace all the j's with I, and then subtract one from the other. The VTs go, okay, when you subtract one from the other. You've got uj minus ui here. You've got a bj minus vj here. This thing is going to be the same after row periods. That's what we're saying. That's what finite dependence means. Okay. So this thing is going to be the same after row periods. So this term is completely going to go. Okay. And so what you're going to be left with is here you've got some stuff, and you've got to do it for j, and then you're also going to be subtracting for the equivalent I. I'll do that one more time. This last term, you're basically summing over all kinds of stuff here. Double sum, see that? Triple sum. See? So what you're doing is you're summing over these things, and how are you weighting them? Well, you're weighting them with the difference between this guy when you start at J and this guy when you start at I. As a result of that, you're only looking at all the P's, all the conditional choice probabilities that go from now out and out until t plus rho. Okay, so that's the idea. That's the result, actually. It actually goes to games as well, although you need some extra conditions on there. Not many, but it is much harder to find, although Peter and I have worked out at least a case where you've got renewal and you can get finite dependence in the game there. Notice that this is defined for choice pairs. It's just defined for I and j at a given xt. That means you get one orthogonality condition out of that. Now, if you can find, if it was true for all of them, if it was true for all xt's, that'd be great. You'd have tons of them. But it doesn't have to be. You're looking for enough orthogonality, as many orthogonality conditions as you have parameters, basically. I mean, that's loose, but that's roughly what we're talking about here. And so you need finite dependence to hold at enough state time specific slash choice pairs. Okay, state, okay, given state, given time period, choice pairs has to have that equation hold for as many parameters as you've got. All right, so basically the point is you end up with this. This is what I've already verbally said, so I'm not going to repeat it. Well, it's half repeat it. You've got the difference in the utilities. You've got the difference in the correction terms. You've got to worry about the finite dependence that goes on when you use I versus when you use j. Take the difference in that, add them all up. See that? That's an equation you can estimate because you got probabilities in there, right? You've got identification on this. In this kind of setup, you may well have parameterized the U anyway. Remember, we talked about linear U's in the X's, so you get a closed form in that case. And so you could, one way of doing this, of course, would be to go ahead and write down these in terms of orthogonality, these as orthogonality conditions with a minimum distance estimator. First estimate the kappas. Those kappas come from the Fs and the sequence that you've chosen. You're not estimating the sequences, you're choosing them, although I'll come to that in a minute. And then you've got the conditional choice probabilities, put them in there, providing you don't have too many parameters, minimize that. You've got a minimum distance estimator, go from there. Okay. So here are a couple of choices, a couple of little examples of this. Terminal choice, and this is used in IO a reasonable amount, where the firm can say liquidate, and when they liquidate, it's all over. So the idea is firm liquidates, and when they liquidate, there's nothing left. And so if you liquidate this period, nothing left. Or alternatively, you can go one more period and liquidate then. And then there's nothing left from the third period. So we're just comparing the choice probabilities of liquidating now versus next period and the utility that you get in the meantime if you don't liquidate. All right. And so in that case, I've just set it up, and I think probably the best thing is for you to look over this yourself. You just set the weights so that that happens. I won't go through it now, but the equation that you end up with is very simple. You've just got the difference between the two choices here. You have the correction factor just for the current probabilities, and then you've got next period's probabilities entering here along with the correction term, and you're done. Okay. So in other words, this completely eliminates in a very simple way the calculation of the value function. Just as we saw in the renewal problem, here's another very simple example. And I've already talked about the renewal case. I talked about that with Mr. Zerker's problem, although I didn't describe it in these terms. And there the basic argument is, as I said before, that the state variable next period doesn't depend on the current state. In other words, when you start a buy a new engine, it does not depend on the state of the old engine. Okay, so that's what's key to about a renewal setup. Another one I'm going to go through in a minute is in a very simple job matching model. It's a renewal problem because when you start a new job, if it's strictly specific capital, or if your general capital does not depend on the job you have, well, it's like starting again, at least with this specific match. Again, we had a very simple equation here. And here again, we're just differencing the two current utilities you get, differencing the conditional, the value function corrections associated with each choice. And then you've got to worry about what happens next period, as opposed to whether you take the maintenance decision now versus the replace decision now. You just worry about what happens next period, then you're done again. Okay. I'll give you one more example. And the reason I want to do that is because I want to show you why this is actually a little bit deeper than it looks. Maybe. Let's not get too carried away. So here's a simple search model. All jobs lasting one period. And I used to say Spain because I thought, well, everybody under 40 can only get temporary jobs anyway, because of the two-tier labor system. So that seems to be a reasonable prototypical example, but really, this is here for illustration, that's all. So you can stay at home, okay, that's the first option, or you can put yourself out on the street for temporary employment by taking action 2. However, you're only successful with probability lambda t of the time, because depending on the business cycle, there are time-varying job arrival rates, okay? And in this setup, you put yourself out on the street, you may or may not get a job for that period. Probability of getting a job is lambda t. And as the more experience you get a little bit of extra human capital, and that kind of increases your wage if you get the job, okay? Very stylized. But you'll see why I'm doing it in a minute. So let's think about finite dependence in this one. One of the things you could do is stay home and then apply for employment, as in put yourself out on the street, with a weight of lambda t on lambda t plus 1. See, the business cycle thing is going to be different next period. Suppose people know it. And that's something that Victor and I were discussing earlier at breakfast. But suppose people know it for now, okay? And you're thinking, okay, let's do that. And then the alternative would be to seek work today. Let's seek work today. We may or may not get it, but regardless, next period, we stay at home, okay? Now, this pair of sequencing one period dependence works, because think about the amount of expected the distribution of human capital 2 periods from now, given that you take this action or pair of actions versus this pair of actions. In both cases, you've got that 2 periods from now, your X goes up with probability lambda t and stays where it is with probability 1 minus lambda t. You can follow through the arithmetic later, but that's all it is. Basic point is that since lambda t is changing, well then to make sure that this is the same 2 periods from now, you've obviously got to apply for employment or temporary employment with different probabilities to get that overall probability the same, okay? So, okay, that's, I think, simple enough. But notice, suppose lambda t is greater than lambda t plus 1. Remember, lambda t is just the probability you get a job, all right? It might be 0.95 today and 0.9 tomorrow, okay? in that case, well, the weight that you put on one of these things, that is, I think applying, is going to be greater than 1 in one case. But if the weight on doing one of the actions is greater than 1, well, then the weight on the other thing has to be less than 0. Okay? So this is a very simple example to show why negative weights arise very naturally in this kind of setup. They might seem kind of screwy, so do complex numbers. They still work, okay? They're not like complex numbers, by the way. So the basic point is that to get these sequences to line up, well, then you might use negative weights. And that's not something that we would naturally think of when we're trying to, I'm going to say, guess and verify whether there's finite dependence or not. That is the method that people almost always use to establish finite dependence. In other words, people think about the renewal stuff, for example. It's easy to see how finite dependence is going to work. It's easy to see in what's called the single action finite dependence case, where you do the same action one period after another in order to equalize things. But in fact, we can't, there is an algorithm. This is stuff that Peter and I developed, that goes between these two procedures. So you're basically checking counterfactual outcomes arising from deterministic choices that might induce or rule out finite dependence, just checking out different combinations without specifying the probabilities. And then having checked out whether there could be finite dependence, then you just go through and ask, well, is there a matrix that inverts or not? And that essentially tells you, well, actually find the rank or not. That's more specific, more correct. So that's how we can find out whether this works in a systematic way. And then one of my students actually has an application of this in opioids, in which he uses this algorithm, in which there's no way you'd be able to see whether there's finite dependence or not without going through the algorithm and then checking it out ex post by following the procedure. And he shows that, in fact, there is finite dependence after 3 or 4 periods, I can't remember, and negative weights are involved. Now, the other application we have, that Peter and I have, is one in which there's a simple game in which the firms can accumulate human capital, but they sort of keep competing with each other in terms of quality of product, stuff like that, but they could lose it all. Where, again, negative weights play a big role. And the only reason we know that is because we use the algorithm to find out whether it works. So we think this actually has a future. It's not just whether you go around guessing whether finite dependence holds or not. There is a systematic way of doing it, and then, but that takes more work. So I want to move on now to the second part of this lecture. First part of this lecture was, can we talk about situations in which we don't have to compute all the conditional choice probabilities? Can we exploit this concept of finite dependence so we only have to compute a few periods ahead and get the characterization of the conditional value functions that way? And so economize on stuff that we don't see. For example, take Ken Walpin paper on people getting education, kids getting education and then going to work. Do we have to assume the same process for wages after they go to school? Or can we find some finite dependence that says, okay, because there's finite dependence, we don't have to observe that stuff in the data. We will just use finite dependence to estimate all of the schooling people want to get, in the first part of their lives, recognizing that they're going to follow some kind of process later on with finite dependence? The answer is yes. And so that's the and in fact the model that they have, I think, is subject to does have that property. I've never checked it out, but I think there's scope there. So finite dependence is very useful when you've got short panels, not so much in the identification, because there you're going to be parameterizing things in the usual kind of way to be able to work, to be able to get somewhere. Not so much in the identification, but in terms of the practical application, if there is identification, because you parameterize things enough, and that's what we often do, to be quite frank, parameterize things enough, and then you're just looking at, well, is there finite dependence holding or not in this application? It's a way of moving forward. Notice that there might be multiple ways of getting finite dependence. For example, if you've got, take the bus engine case, replace versus not replace, okay? Then we said if you replace a couple of periods from now, well, then you get finite dependence. But here's another way of getting finite dependence. Choose replace, choose not replace. Now, then choose not replace, not replace, not replace, not replace, and then both replace. Okay, you get 5 or 6 period finite dependence that way. Why you would want to do that, I'm not sure. Okay, yeah. Not renewal, no. That is for this example, there's renewal. And the reason I use it all the time is because it's so obvious that you're getting back to the same thing. But remember, we only need the distribution being the same. And so go back to that simple search model that we did, just the distribution. And typically they won't be the same because after all, there's a stochastic process driving what happens. Okay. So it is the distribution that's the same about that surplus. There's a social surplus function out in the future that depends on X. Well, which X are you going to get to when you follow one path or the other path? You're just going to make sure that the distribution of that X is the same at the end. Okay. That is what's critical. Of course, you should ask whenever you want. All right. Okay, let's move. You start relaxing this conditional independence assumption. It's wow. You open up a multiple integration challenge if you're dealing with this as just breaking that conditional independence assumption and looking at the joint distribution depending on a couple of stuff. So I want to give you an example of that and give you a sense of what's involved if you do maximum likelihood. And then I want to simplify the case to situations in which there is unobserved heterogeneity, but it's exogenous in the sense the process of unobserved heterogeneity is not driven by selection. First, I'll give you an example of what happens with maximum likelihood when the unobserved heterogeneity, the unobserved random variable, is actually driven by selection. And then we'll say, that's too hard. And then go back to this setup. So after I estimated this model, and Ariel Parkes estimated his model on patterns, which also has unobserved heterogeneity in. We were sitting in a coffee house together. This is the late 80s. And Ariel said to me, I'm never going to do one of these things again. That is a sense of what it takes to do maximum likelihood. Of course, things are much faster now. Computers are much faster. Theodore and Bertel are going to tell you, hey, maybe. But the point is, it is much faster. And so that does increase, the computational limits and are much less restricted now than they were. And so I don't want to overstate the case, how difficult it is, but you should be aware that there are at least computational trade-offs involved. Okay? So here's the setup. And I'm going to describe it intuitively to you before I bother with the slides. You've got a bunch of jobs that look exactly alike to begin with, and you are Robinson Crusoe or whoever, Friday. You're picking, well, what's this fishing hole look like? To switch the game to what does the next fishing hole look like, et cetera, and there are an infinite number of them. You just keep on choosing until you find one fishing hole, never runs out, that you're comfortable with. Okay, so you're looking for the best spot, if you like. Now you could search forever, of course. You get experience when you're on that in that fishing hole, but of course, at some point, the problem of getting enough of continuing searching is just not worth it, given that you have found something that is good enough. Standard search problem, it's just the only thing, well, it's not really, it's standard, but the way you discover how good the match is by experiencing it. You don't see it straight away. In a typical search model, you get one simplest search model, you get one draw and you decide whether you take it or not. Here, you take something that looks the same as everything else that's new, but then you just experience it, see what your employer's like. Do I stick with him or her, or do I move on to another job? Okay. You could have general human capital associated with it, but again, that has no role in what I'm going to talk about now. So the idea is that you draw a job match here, but the payoff is not just a job match, but also a random shock as well. And you only see the payoff that you get. Could be, and here I'm thinking more of non-pecuniary utility associated with this, because you might imagine that you know what the wage schedule looks like. It's just that you don't know how much you're going to like the employment position that you're in right now. Now think of what you're going to do here before we get to math. Think of what you're going to do. You're going to basically take something at random, okay? And then if you get a good enough draw, well, you're going to stay on, okay? You will update what you think your job match is at the same time. Take another draw from the same match. And then you're going to think, okay, if it's bad enough, I'll definitely quit and start again. What's happened to me in 2 periods? I've got 2 periods of 2 periods of experience now. So I am going to learn much less about the current job that I am in right now than what I would learn if I switched to a new job and started again. So when I'm starting with the very first job, I'm thinking I'm getting both payoff plus information as I learn about it, okay? As I move along getting more experience, it's the payoff that counts. Extra information, you've got to be kidding, okay? Whereas if I took a new job, well, there would be the information and payoff. So the only reason I'd stay on in the old job is if after I've updated my beliefs, my expected value or the distribution of this would be high enough that it's not worth learning something else. Okay? So that's what's going on here. You start out. If it's good enough, you stay on. Otherwise, there's a cutoff point. You just get rid of all the people who have a posterior, Bayesian. Posterior are going to drop out. They get more information. Those guys, more information. Now, instead of having a truncated distribution where it was cut out, you get some spread again because you're taking that truncated posterior, truncated because some people have quit, okay? They're all getting another normal draw. So you put a normal draw with a truncated normal, no longer simple Bayesian rule, of course, it's numerical, okay? You now get a posterior distribution over that second one, not getting as much information the next time, so you're having a higher truncation point than you did before, goes like that. All right. So that's the setup. Randomly pick a job match. You see the payoff at the beginning. You've got a degenerate distribution over everything because there are because at the beginning you have the same match over everything, and the normal the mean is the same, and so you're going to update using Bayes' rule, and this is how you're going to do it. Take my word for it for now. And then you're going to be comparing the value. I'm going to call it the value function of going one way versus the other way. Doing that. And maybe I should put it in terms of value functions, but I've stuck with the original notation. In this case, you can use something called a Gittins index to talk about what's optimal. And it's worthwhile mentioning that briefly, because if you're talking about things that are independent of each other, then you can form an index for each of the different things and then just compare the values of those indices and pick the one with the highest index. Now think about a value function that you'd face if you're comparing a whole lot of different options. You're going to have all the state variables in there, in principle, right? Now, suppose someone told you, no, you don't have to do that. That's easy. It's much easier than that. All you do is solve for a value function, which I'll talk about in a minute, a value function for each of the things individually. So I've got to tell you what that problem is, okay? You get the social surplus function for each of those individual things. That's a number for the given the values for the parameters you've got. Compare the indices and then just go with the optimal one, okay? Go with the one with the highest index. That's a much easier problem to solve because obviously you've reduced the dimension of the value function from everything across to just looking at compare the indices one by one after you've calculated the value function for each of these things individually. And the reason for that is that when you add state variables, it doesn't grow linearly, it grows exponentially. It's just huge, okay? Whereas if you're comparing across indices, well, then that only grows linearly with the number of jobs, okay? So what is the problem in this setup? And this is the sense in which that question about renewal is kind of germane, because in this case, what you're really looking at when you're looking at an index, you're basically saying, okay, suppose I start and solve the value function for this one, and then I keep on going and solve a renewal problem associated with that one. What would happen in that case? So it's a renewal problem for the bus engine that basically gives continuation value for these guys. And instead of doing it that way, we've just got, which is the same thing in principle, and mathematically actually, is just saying, well, what is the expected net present value of going forward divided by the discounted value of dollars that I'll get when I just have $1 per period and then beta squared, etc. See that? This is just discounted time. So we net present value over discounted time, all right? Because it's not simply that the dollars don't count as much. There's a sense in which, I'm going to say intuitively, but I'm not sure whether it is or not, the periods don't count as much either. 2 periods from now only counts as beta squared. 10 periods from now count as beta to the 10th. And so it's kind of like an average return where the periods as well as the dollars are counting. And that's the way you can, that's the way you can turn this into, when you take the maximization, if you soup over these guys or max over these, you get the optimal, you get the index out. And in this case, you've got a normal distribution helping you. And so basically here's your prior now, and here's the information value. And the more periods you've got here, the less valuable that information is. I mean, there's more to it than that, of course, but I'm just giving you an idea of how to think about optimality in this kind of situation. Doesn't always arise, but I've seen applications where this applies and yet people haven't used it, and that just makes it harder for them. Okay. So then it's, given that's the optimal thing to do, this then becomes, and you can think about these as continuation values if you like. Here's the business of starting again. Here's the business of the social surplus function from here on out if I stay with the current job. So it's essentially the same thing. And so let's go to the hazard function. That's the probability of quitting, because people are learning about themselves, but as they learn about themselves, they discover this job is not for me. I will try something else. So if in fact they discover this job is not for me because starting again makes more sense than staying on the current job, that's just like saying, here is the distribution of what these what my expected value of the job match is. If it's less than some amount, and there all I've done is difference these guys, in that case, I will quit. And that is the probability of quitting, of course, at that time. In other words, conditional on reaching this point, do I quit now? I quit now if the expected value of my posterior is not high enough relative to changing again when I get my information, and versus staying on and learning a little bit more. And I'm just going to call this thing horseshoe T. And that is just going to be the cumulative distribution of this. And so here we have it. Here's the distribution of the gammas at this point, and then you quit if it's not big enough. That's given by that. And so at the beginning, well, this, by definition, will normalize this to be equal to 0 for everybody. And so the distribution just looks like this. Watch my hands go like this to 0, and then up to 1, and then across. Okay. And then, so it goes like that. There's the cumulative distribution function, actually. All right. Excuse me. Should have had a mirror. And then after I've done experienced one thing, it's going to be a little bit sort of, it's going to be smoothed out, cut it out again, smooth, all right, cut it out again, etc., etc. And so we got to get that distribution thing, all right? This is the value of not doing things on a screen, right? Just in person, we can do the hands. So every match survives one period by definition. So here is our posterior mean, UN, if that is small enough. And so the probability that it ends is just given by this norm. This is just the normal distribution, the cumulative normal distribution evaluated here. It's going to be greater than a half. The notion is that half the people are going to discover that they're below the mean anyway, so they will want to quit. And some of the other people are thinking, even if they got a posterior that was bigger than 0, it's not that much bigger, and there's less information, so they leave anyway. So that's why this thing is going to be greater than half. And then you just keep going, okay? Here is you start out with a distribution of this guy. It's in here. You integrate over what's going to be the epsilon draw next period. Calculate this guy. And so in the end, you've basically got this kind of distribution where you're calculating the posteriors of the survivors here after T+1 periods now. And then you've got the distribution of the posteriors for the T period survivor. And then so far as the T period survivors are concerned, a bunch of those guys are truncated, they get to draw stuff, and then the issue is, well, are they high enough? And you get that hazard function there. And what you can see is straight away the problem of multiple integration. Because each time you do one of these integrals, you're going to introduce approximation error. And so the more times you do that, the messier it gets. So the approximation error accumulates, okay? And that's a basic problem with doing this multiple integration. There are multiple ways of trying to get around this, but that is the basic problem that they've got to try and solve in this situation. And the idea is that multiple integration essentially involves a multi-dimensional object. So the more dimensions you've got to get at, the more cells you've got to fill in, okay? You start with a square, you go to a cube, you go to time, and then I don't know what, okay? So in terms of thinking about those extra dimensions. So that bugged me, all right? Still does. To the extent that fixed effects can handle this, great. You know, there's an issue there. How do we move? So in this setup, if you can do the multiple integration, well, then it's straightforward from there, because now you're just getting the hazard rates at each time. You're forming a probability that people will quit after tau periods. That means that they didn't quit up till now, but they do quit now. So you've now got the probability that they'll quit after tau periods. You've got a maximum likelihood estimator that comes straight out at that point, okay? Notice what's involved. You've got to get the optimal rule. Gittins helps you on that one. And then you've got to do this multiple integration to get the hazards out. You do that, and then you get the probability of quitting, and that then leads you to calculating the maximum likelihood estimator. Now, I just went to ChatGPT to see whether this would work. It told me, oh, it's simple. Just take a bunch of hazard rates, put them together, and you get a good approximation. So AI might work in the future on some of these problems, but it doesn't yet work on a problem that's 40 years old. So there is future there. Don't get me wrong. I come from Carnegie Mellon, where we advertise this stuff like crazy. But it's something to be aware of as you sort of think about how do you incorporate AI into sort of these kind of structural estimation problems. So don't mean to be negative, but it's clearly that there's a combination of human intelligence still involved. Okay. Yes, I think I've convinced you. It could be quite cumbersome, maybe unmanageable. How about we start with a simpler problem? Can we get away with something easier? All right, so let's do that. Here is Mr. Zerker again. Served a great service to humanity. He's going to replace the engine or keep it. Fast filage is going to follow the same thing as before. We got a type 1 extreme value, and away he goes, estimating its social surplus function. But now the type of bus is unobserved to the researcher. So somewhat facetiously, John got it wrong. He just didn't see that there weren't just GMs, but also Fords, because his data set didn't show that. Now, I know that's not right because John was at Wisconsin at the time, but let's just pretend for now that there are both Fords and GMs here, okay, as opposed to one type of bus. But we don't see it in the data, okay? So we have unobserved stuff going on, and you can see the maintenance cost depends on what type of bus it is. So Subaru is a great, Jeep's horrible. I've had both cars, all right, in terms of maintenance costs, okay? How could we go about this without going through some of the stuff that I've talked about before? Well, I'm going to take an adaptation of the EM algorithm in which we imagine, well, we say S is unobserved, but let's start out pretending that we know how to evaluate the conditional choice probability of all the state variables that count, which is how many miles has the bus got on it, and also what type of bus is it, okay? We pretend that. And I'm only doing that pretense so that I can introduce the way the algorithm works. So in that case, we could go ahead and say, well, here's the probability density associated with being in an unobserved state S. Suppose for now that beta is known. So the maximum likelihood problem for this, what I'll call easier problem is, well, here are the different states you might be in. Okay, might be more than two. All right. Here is the likelihood function associated with, given the state that I'm in, what is the likelihood function derived from the joint density of going through all of these different time periods for that particular bus. See, remember we got a fixed bus, and it is Ford doesn't change into GM and vice versa. It just stays there. It's fixed effect, right? Not fixed effect in the sense that Victor was talking about, but time invariant effect. All right. And so in that case, the more we observe of a given bus, the more likely we can distinguish the buses that look like they're GM because they're getting their engines replaced all the time, say, versus the Fords, which hardly ever get their engines replaced. So we can sort of divide them up that way because they have different engine replacement costs. All right. So conditional on knowing what type of bus, what is the path that we'll observe? We don't know what type of bus it is. So let's just integrate over this probability distribute wherever it is. Probability distribution of, there we go, of being an unobserved state S. Just maximize the log likelihood. Go ahead, choose the parameters of the utility function, that's the replacement cost, and also this distribution here. To maximize that, we would have the maximum likelihood estimator at that point. Okay? That's, say, if we knew this somehow. All right? We knew this. One way we might know it is because we might compute it for every set of thetas. So that might be one way of doing it. But let's suppose we just know it. And then in that case, we could use what I call the quasi-maximum likelihood estimator yesterday. And then what we would be doing is just plugging. So God knows how we get this thing if we haven't already computed it. But again, this is just pretense. We get a logit here, okay, where we've plugged in the difference between replacing versus not replacing with those log odds. This was that dynamic correction factor that I was talking about last time when I went to the estimation for that Rust problem. And then we just go ahead, maximize, and we're saying could be computationally burdensome because basically you've got inside this log of these products and sums, which is going to be numerically a pain in the ass. Okay. So instead of doing that, how about we do the following? At the nth iteration, because we're going to go, right? At the nth iteration, what is the probability of this bus being a type S conditional on all the miles that we've seen, all right? And we'll see for this observation, along with the thetas that we somehow got in the previous iteration. And of course, its state right now, the number of miles it's got on the current clock. Actually, excuse me, all the miles that it had when it was replaced. So this is all the data for the nth bus, okay? Both replacements and miles when they were replaced. Along with Well, what was the probability that it is a type S bus to begin with? And the conditional choice probabilities all the way through. In other words, given all the information that we got from the previous iterations and all the data that we have on this bus, what is the probability that this is a type S bus? Given everything we know so far from the nth iteration, and including the particular information that we have on the bus, what's the probability it's a type S bus? Well, that can be calculated from the joint distribution. In other words, this is the joint distribution that here is the probability that we're going to see all of these replacements and the x's from t to t for the whole string. This is a likelihood for the whole string. Okay, conditional on S, the time, times the probability that you are type S. So that is the joint probability distribution of being both a type S and seeing the whole sequence of everything for that bus, given the thetas that you've got from the last iteration. So that's what that is. And so is this. You bring this up to here. That is another way of expressing the conditional distribution. Okay? Because the basic point is that this is the marginal distribution of observing these miles when we're integrating over the possibility that it could be one of these types, and then you're hitting it with the conditional that it is a given type. All right? So that's how we would potentially compute this thing if we knew how to get a likelihood. And then we're going to just say, well, how do we update this guy? Well, it is just the average of all these things, okay? This is just applying the law of iterated expectations, but more generally, we're thinking, well, you take all those buses, what's the probability? What's the overall probability that they're one or the other? Well, that's this. And then we go ahead and say, okay, let's just go ahead and calculate this theta n plus 1, in other words, the next iteration of theta, by maximizing over theta now, looking at the buses, summing over the different types, reflecting the fact that we've conditioned on all of this stuff, and looking at that likelihood. That's how we do this thing. So here's how it works. Set some initial values. Here is initial value of theta and some conditional choice probabilities. How would you do that? Well, first thing I think you would do is estimate the model without any unobserved heterogeneity in it, okay? Just ignore it. And then say, okay, let's spread it out a little bit because there's no real reason to suppose that you're starting out with good estimates. Love to start out with consistent estimates whenever you can. Because if you start out with a set of consistent estimators, well, then some of the stuff that Victor's going to tell you about later, because you haven't done it yet, is going to say, well, you only have to do one step. Now, you might argue for more, but you actually only have to do one step to do that to get that asymptotic efficiency. And so starting out with a consistent estimator is going to put you in the right neighborhood. And then from then on out, it's all local. Okay. So you compute this thing in the way that I've just described, and also the pi as I've just described. Now you're going to update the conditional choice probabilities using one of the rules that I'm going to describe in a minute, and then you just maximize away in terms of the theta that you go through. Okay. So that's the basic idea. You start out with no unobserved heterogeneity. Then you say, all right, let's spread out the parameters. Maybe you're going to use a confidence interval or something like that to say, well, instead of being the point estimate of theta, maybe we could spread it out a little bit. Maybe we could spread out the pi's a little bit. That's how you would think about going about this thing. And if you go about that kind of setup, you can, I'm going to say, more or less show that you can converge to a local optimum. Now, there are two problems with that statement. First of all, there's the more or less part. And second of all, there is the local stationary point, local optimum, as opposed to global. So that suggests straight off from the second point that you're going to have to start from different variable, that you're going to have to start at different kind of initial points to be able to get global optimality. And I don't like that because then, of course, it's discretionary as to how many points you choose and where you start from. I understand that. The second thing is I said more or less. Well, we can only show in one of the versions of this EM algorithm that it is strictly monotone. Okay, that the other algorithms are not. We can't establish strict monotonicity in one of the steps, and so that is also another challenge in terms of thinking about implementing this in general. Okay, so yeah, it works just fine for the simple examples that we've got. There is a job market paper this year in which you've got a much more complicated problem instead of just doing a simple Monte Carlo, and she seems to be just fine with what she's getting. So that gives hope to future down the line. But I want you to be aware of those things. All right, so the two rules are pretty straightforward. Oops. Sorry, I'm going the wrong way here. I'll find it in a minute. Yeah. One way. Firstly, you just use this kind of quasi-likelihood function that I'm talking about. Not the real likelihood, of course, because we're just plugging in the probabilities instead of the value functions. So it is a quasi-likelihood. Okay. The second thing is the second rule, which in some ways is, I think, more interesting. How do you think about the CCP in this situation? Well, first of all, if you knew what kind of bus it was, if you go back to the Qs here, this is the probability of a bus being a particular type given everything you know about it. Well, suppose you actually knew what S was, 1 or 0. You observed it. All right? What would this rule come to? Well, you're putting an indicator function here as to what type of bus it is. And then you're also asking, does it have this many miles on it? And then you're saying, of those kinds of buses, here it is, of those kinds of buses, which ones replaced their engines and which ones didn't? So this probability would simply be the probability that you get when you know the type of buses, or the relative frequency when you know the type of buses. Now let's look at how that extends to the case that we're concerned about, in which you don't know what kind of bus. Now the Q is not a 1 or a 0. If you knew which type of bus, Q would be a 1 or a 0. Okay, that's how I got this denominator and talked about the fraction of the buses of the right type with the miles on it, whether you replace or not, to get this conditional choice probability. Now we say, okay, we don't know. Could be half Ford, half GMM. So we put a half here and a half here. It counts as half a GM bus because we don't know whether it's a GM bus or a Ford bus. So maybe it's a 3/4. And we're almost sure, well, 90% maybe on this particular bus that it's this one. So we count as the 0.9 that it's a GM bus, say, and therefore take the miles very seriously, or the decision very seriously. It could be 0.1, maybe a probability of being a forward. And so we just put a 0.1 for the forward, and that's how we get these estimate for conditional choice probabilities in there. Okay, so it's a very intuitive sense that we're weighting each observation by our best guess in terms of the iterations that we've already done as to whether it's one thing or another, to see how much it counts when we're thinking about what decision is made to replace it or not. Okay, fine. So that's how this thing works. Update that way and go for it. Same kind of Monte Carlo as we did before. We've got stochastic stuff going on in terms of the number of miles. Equally weighted. This is where the equally weighted comes into. It's a half-half initially, half of them are forward, half of them GM, but they have different costs. Then you get this, here we go with the finite dependence thing, V1, V2 minus V1. See how we've got just one period finite dependence as we move one period forward there. Go through with that. And then we say, okay, what happens? Well, first we know that if you ignore unobserved heterogeneity when you really have good reason to thinking it's there, and in the Monte Carlo, you know it's there because you put it there, okay? Then you get some serious bias in this stuff. Notice that the intercept goes up because nothing explains, things aren't as explained as well anymore, so it just gets blurred. Secondly, mileage doesn't count as much anymore. And those are the main thing that happens. You can see that the estimation still goes up quite a lot, an extra couple of hours here. Here you're going up not from a few seconds to a few minutes. Notice that, because you're going through that iteration thing. And so you've got to calculate the CCP estimator each time, okay? And so it takes, I don't know, about 50 iterations in order to get from here to here. And so that's the sense in which it's sort of linear in terms of the number of iterations it takes. If you divided this by that, you could basically get the number of iterations. There's a little bit more to it than that, but not much. And then with the time effects, if there are time effects in there as opposed to just a stationary model, that increases it even more. Now we're going up to 11 minutes. Still not a big deal. And so for serious problems, as opposed to this toy problem, we are still estimating the beta. As opposed to this toy estimator, it is doable these days. I haven't got a serious application though, but this Yale student does. So remaining 7 minutes. Move on to another one that Victor's going to expand on later on. We are actually connected. We argue with each other. I mean, all of us, but we also cooperate. Sort of works both ways. And you will find that in your profession, that there's something called co-opetition. Sometimes assisting, sometimes working against, that's part of life. Suppose there are a maximum number of firms any one time. We'll count it as cap I. Here's the number of firms. Firm exits, next period an opening occurs to a potential interest, to a potential entrant. And you've got a one-time chance to come in or stay out. All right. So think of this thing. Oh, wow. Look at this. Ta-da. Old school. And it sort of works. Try a different texture. Oh, even better. Squirrel Hill, where I live in Pittsburgh. There are little shop spots all along. They all sell different types of ethnic food. Just like at home, not as good. And you can either stay in or get out. And if you get out, that spot comes open. Next period, someone else can stay in or get out. Right? And that's how it works. And that's how it works in Squirrel Hill. Maybe here too, I don't know. And so basically, there's a fixed cost of coming in, all right? But once you've paid the fixed cost, you are in. And so you don't have to pay that fixed cost anymore. All right. Now, whether you come in or not, it's going to depend on, say, this spot is open and this guy is thinking about coming in. Whether you come in or not is going to depend on the number of spots that were occupied last period. So let's think of just after COVID, no shops open. All right. So you might imagine that someone thinking about coming in, yeah, I'm not going to have very much competition because even there are a bunch of other people that might be coming in. They all got to pay the entry cost too. Maybe they got a bad draw on their entry cost. Maybe they won't come in. So I'm not going to have as much competition. They're all going to come to me. Hey, I'm going to come in. On the other hand, suppose everything's been saturated because we had the first wave of people coming in after COVID. And now we've got all the restaurant spots occupied again. There's just one open, and the guy who's thinking of coming in thinks, oh, I'm going to face all this competition. I have to have a really good draw on coming in, specialty food, whatever, I don't know, in order for me to come in. Okay. So that is the situation in this world. There's going to be a demand for food. It's going to depend on how many people are there. There's going to be a fixed cost associated with coming in. And we're going to play this Markov equilibrium, Markov perfect equilibrium. Okay, that's what's going on in this setup. Now, it's going to be a little bit complicated from that, though. You see, I don't observe which markets are doing well, which markets are doing poorly. And so this state, this pi t, I won't do this anymore, is going to this pi is going to determine the how good the market is, or it's going to be one of the determinants of how good the market is. And there is a probability that the market will be the same this period, the probability of every other state being equally likely. So just one more little thing. Down the main diagonal, you've got pi's. And over here, you've got the 1 minus pi's divided by whatever number of states there are. I think it's 4 or 5. Okay, 4. Okay, so all of these elements up here, all of these elements down here have the same value. And here it is pi. And so that's how it works. So a very simple Markov process describing how the market is moving exogenously. So notice that I've moved from a situation where it's a Ford or a GM to a situation where Ford might morph into a GM and GM might morph into a Ford. Okay, think caterpillar, butterfly, whatever, although not very many butterflies turning into caterpillars, but so what? In any event, think about that kind of morphing going on, or this kind of state going on, limited variation, exogenous, but still movement as opposed to time invariant. So price is determined by the number of firms in there. There's a permanent market characteristic. There's this Markov demand shock that I've just described in terms of how the S's move. And then there is also these temporary shocks that help to give you some sense of what happens to the market. So here's a price equation, clearly depending on the state and also the number of people in there. So obviously this alpha 3 should be negative. The pi is going to affect demand. I mean, the S is going to affect demand driven by this guy. And then there's the time stuff as well. So that's what's going on there. We've got some costs. Exit costs is 0, we'll assume, from liquid firms. So there's no, you just get out, you get 0, normalize that way. Current costs, current profits are then just going to be driven by, here are the number of people in the industry, apart from you. Here are the the other factors that affect demand. Here's an entry cost that you pay if you come in. Okay, it's described a little bit further down, but that's basically the entry cost that you pay if you come in. And then you're thinking about, well, do I come in or not? Just work it through. Type 1 extreme value. We got value function being, well, do I stay if I'm in there? Conditional value function of being active. Do I stay in or get out? Well, if I get out, maybe I'll get out next period. And so then I've got the terminal, it's got a terminal value property in that case. So if I stay in this period, I get out next period, versus if I stay out now, 2 periods from now, I'm out anyway. That's the terminal value property coming in. And so that's how we can get these, the conditional value function, just depending on the probabilities of the state of the next period state. See, this is next period state, conditional on this period state, and also ST, go from there. We set the number of firms in each market to 6, so 6 of these guys, and simulated it for 3,000 markets. So we're giving ourselves a lot of room here. Petroleum, perhaps, with gas, think of gas, groups of gas stations in different parts of the US, maybe. That might be something that we might think about. We set the VAT discount factor in this case. We first solved the model just in terms of pushing through those probabilities until they didn't change, one period after the other. And that turned out to be fairly straightforward in this setup. There's no reason why it should be. Yes, sure, it might be unique, but there's no convergence theorem on that. But in this model, it's easy enough to get through. And then after we found we got basically an ergodic state in terms of things settling down. You've got to wait in the data. If there's a new innovation going on, for your econometrics, you've got to wait until it's a stationary distribution. Otherwise, all those isolated points that you get up there are playing a role in your estimates, but in fact, they're not part of your asymptotics. So you have to be careful about that kind of thing. So we rolled through, ran this, just used the last 10 periods to estimate the model. And this is what we got. I realize I'm over time, so I better stop in a minute. We roll through, this should be a minus here. There's a typo there. And then if you work through this, you'll see that if you ignore what's going on, you get some pretty serious bias again. And we tried different types of using the CCP estimator, more or less with different variations of different variations of the method that I showed you, but all very similar to each other. Let's do that. Let's describe it that way. Both including the demand and the also the case where we didn't estimate the demand equation at all. And you can see the estimates are pretty close to, quite reasonable. You can see how much the time goes up to. We're talking up, depending on which variation we're talking about, goes up 21 minutes here. These are, of course, this is nothing in terms of time. And for serious applications, like for the stuff I was doing yesterday, we're really talking about several days to really do the estimation. Not months, days, but it does take a while, and that's even when you send it up to the cloud. So that gives you some idea of how you can deal with unobserved heterogeneity to a limited extent, at least, in not just individual optimization problems, but also in games and its time and stuff. So thanks.